The mean value theorem actually has a lot of consequences. Because it's a thing, a lot of stuff just starts to come out of it. There's so many applications that come out of the mean value theorem, which we call corollaries, which are basically things that come out of a theorem, or like this idea that comes out of this theorem, a mean value theorem. And we're going to talk about some of those consequences, known as corollaries. The first one has to do with increasing and decreasing functions. So increasing and decreasing. Because of the mean value theorem, we can actually define what an increasing and decreasing function looks like in terms of derivatives. Okay, so what happens? Let's say if I have this interval a to b and it's differentiable, so it's defined on a to b, differentiable on the open interval from a to b. If f prime of a value, whatever value, is greater than 0 at every point in between a and b, we call it an increasing. It is increasing. So what it says is that if the derivative is positive, typically when we say positive, this is how we denote something to be positive. It's just greater than 0. If it's always positive at every point a to b, it increases on that closed interval a to b. And let's just look at a quick example. If I have this function here and here, and if at every point it's somehow increasing, then we say f is increasing on that open interval. It's a very simple definition. This is another example. Notice that it can never start decreasing randomly. It can't do this because it's decreasing sometime, but it's only increasing. So these are some examples. And then conversely, if the derivative is less than 0 or negative at every point from the interval a to b, the open interval, f decreases on the closed interval a to b. So again, quick example, we have a point here and we have a point here. We have an example being like this. This is always decreasing. Another example, it could be this is the straight line path, and another example can be this. It starts slow decreasing and then just dramatically decreases. And again, we can't have any point of increase there, or else we can't call it a decreasing on that interval. So that's the idea of that. Let's also define what I mean by increasing, right? Because, I mean, graphically it just looks like going up, but there's actually a technical definition. For this one, let's take two random points, let's say here and here, and let's call it x1 and x2. Increasing is defined like this. So since this is a greater value than x1 from the graph, this must also be true. In other words, since it's ahead of x1, since x2 is ahead of x1, the value of x2 must be greater than x1. And this can be for any value as long as these two conditions hold. And then the opposite would be if I take these two values here, so x1 and x2. Since x2 is still ahead of x1, but then it's the opposite inequality. So now the original one is higher up than the one ahead of it. And that's the idea of decreasing and increasing on some I or some interval that are within I, or some points that are within the interval I. That's the first thing that comes out of it, and we're going to just look at more intuitive approaches to these corollaries before you look at it analytically. The second one actually has to deal with functions that are of this form. This is the next one. F prime is 0. The slope is 0. What does that tell us about f? It tells us something. If we kind of think about the opposite of a derivative, if we take a derivative of a constant, it gets to 0. In other words, f must equal some constant. I'm going to give it a c. So what this corollary says is that if this is true, so if f prime is equal to 0, let me say f of x is equal to 0 at each point on an interval I, just some interval, so define a to b, then there is a constant c for which the original function, or f of x, notice that this is f prime and this is f of x, is equal to c on all I. In other words, if we look at this graph, let's say it's a constant value, like this. That's not a great constant value. Flat line, right? We take its derivative of the function, we get something that looks like this. This is 0, basically, right? So we had differentiation. I guess the opposite, this is the corollary. So if we do the opposite of a derivative to this function right here, we get some value c, because if you take a derivative of a constant, it's going to be 0. So it's kind of like reversing the process. And that's the idea of the second corollary. And it's important because it actually sets the stage for the third corollary. The third corollary talks about derivatives and how they're related to each other. So let's start with this fact. And let's just do some thinking about this one before I tell you what it is. Let's subtract both sides by g prime of h. So in other words, I get this minus this is equal to 0. And let's define a function h that it's like this, which is still equal to 0. If I did that corollary 2 to h prime of x, notice that if I did the opposite, it's going to be h of x is actually equal to some constant. And then the same thing, if we reverse this process, we would actually have to reverse the process for all the other ones. So it would be f of x minus g of x. And then now we can solve back to f of x. F of x is equal to, I'm going to add both sides to g, so it's going to be g of x plus c. What does this mean? This is kind of like, it seems kind of weird that we did this in the first place, but there's actually one reason why we did that. If the derivative of f and the derivative of g are equal to each other on some interval I, then there is a constant c such that f of x is equal to g of x plus c for all x in I. And this one is very confusing because this is kind of a weird statement. But notice that if we take the derivative of both sides, we get back to our statement from the beginning, because the derivative of a constant is 0, so that goes away. And basically what it's talking about is doing the opposite. What happens when we do the opposite of differentiation? If we do that, we have to keep track of something that was 0 being a constant now. So in other words, these functions differ by a constant. If they have the same derivative and you want to do the opposite, you need that plus c, or a plus constant, because of corollary 2. And that sets the stage for this big idea. This is the next big idea, called anti-differentiation. So that's a long word now. Differentiation, we know you do apply a derivative. Anti-differentiation should say the opposite, right? So that's the process of anti-differentiation, what we did here. If we anti-differentiated both sides of this statement, we would get this statement right here, because they differ by a constant c. So that means there's a whole family of functions that g and f can be. So let's look at a quick example. Let's find the antiderivative of x. Let's do an 2x. F is equal to x squared, right? So if we take the derivative here, it goes like this. But then there's this plus c that I have to add. Because if I did this process backwards, notice that any c can easily go back to here. And c can be any number. It can be -1, it could be 0, it could be pi if you really wanted to, e, any number. That's the process of antidifferentiation. And antidifferentiation is actually so important that the second half of calculus is actually based on antidifferentiation methods. So we actually discovered the second part of calculus, which is antidifferentiation. If the first part was differentiation, the second one would be antidifferentiation. And we'll actually understand what I mean by antidifferentiation when we get to it. So it's important to understand antidifferentiation in that when you take an antiderivative of a function, you always get this plus c attached at the end. And those are the three corollaries that spawn out of the mean value theorem. It's interesting, I would say, because the mean value theorem was just talking about average values, but then three important things come out of it, and that actually leads us to the second part of calculus, which is antidifferentiation. So very interesting. So that's it for this video. I hope it made sense, these corollaries, and hopefully these pictures made sense also, because they're usually really helpful in understanding the value theorems. And pretty much most of calculus, pictures usually help. So that's it for this video.